So I'm David Ceperley. I'm going to give a first lecture on random walks. Probably a lot of you people have already done Monte Carlo. I guess I don't want to embarrass people by asking if you haven't, but I'm going to assume that you haven't. But please ask me questions. Maybe I'll try to go fast and get to the quantum Monte Carlo part. But we did want to, and if people haven't been doing Monte Carlo, then it's a different kind of a method, because other types of methods, you're used to calculating things and you get things to 6 decimal places or 8 decimal places. And you can see that it works or whatever. With Monte Carlo, every time you do it, you get a different answer. And it's a statistical method, and it takes a little getting used to. And you also have to learn the vocabulary, like we say, is this within error bars? You have to know what that means, and you have to know that whenever you give a Monte Carlo result, you have to give the error bars. And so that's what I'm going to talk about first of all. But please ask me questions if you have a question. We have plenty of time for this. And so I'm going to talk about a little bit about Monte Carlo and random walks. All types of quantum Monte Carlo are Markov chains. Talk about Metropolis rejection method, which is the first thing we're going to cover, and talk about how you calculate error bars. As I said, that's really the key thing that you have to learn to do is the error bars, and give error estimates. Okay, so what is quantum Monte Carlo? What do we mean by it? Well, it's actually a broad technique. It's actually one of the most powerful algorithms for solving the quantum many-body problem. It's quite a general method. And you can see there's a whole bunch of different quantum Monte Carlo methods. We're not going to talk about all of them because they're not all in QMC pack. But why quantum Monte Carlo, or why Monte Carlo, or why simulation? Well, the reason you do it is that it is the most powerful general method to solve many-body problems. By many-body problems, we mean problems that you have more than 3 or 4 particles. So an explicit method, like configuration interaction or solving a differential equation, you have to represent the whole wave function in some basis. And it's easy to, it's possible to represent a 3-dimensional function on a grid, But for the wave function for an electron problem is 3 n-dimensional. So once n is greater than about 4 or so, you just can't represent the whole wave function. So instead we do something, we sample it. And it's no different than in classical statistical mechanics. Like if you're familiar with doing like a liquid water, or a solid or whatever, the most general techniques are Monte Carlo molecular dynamics techniques. And that's the same reason we do quantum Monte Carlo. You do like a Monte Carlo simulation of water or molecular dynamics because you can do it, right? And you cannot do the many-dimensional integrals that you need in statistical mechanics explicitly. No general method has been found. I mean, the type of things that you learn in your classes for ideal gases, that works, or harmonic oscillator, but when you're talking about a general many-body problem, you just can't do the integrals accurately enough. But the idea of a simulation is you put the particles in and you move them around, kind of like nature does them with statistical methods, and then you take averages, right? And so you get a result within an error bar. And it's an exact result within error bars. Within that, it's just like an experiment. The experiment measures the exact properties of your many-body system with some caveats within your precision of the experiment. Now, the difference with computers, and this is really important because of Moore's law, is we can do a lot of averaging. We can, our codes run kind of at the machine rate of, billions of multiplications a second, And so we can generate, say in 1 second, we can generate a new configuration or whatever. It depends on how big the system is. And so we can generate, if we run for a year on a computer, we can generate millions of steps. And that, so that means the error bar can be quite small, right? And so that we can, the thing about in quantum mechanics, as I will explain later, is the error bars are determined by something called the zero variance principle, and they can be quite small if you have a good trial wave function. And so, we can get 4 or 5 decimal places often. But I was trying to say, why do we do quantum Monte Carlo? Well, it's the same way as you do in classical statistical mechanics. I mean, from the correspondence principle in quantum mechanics, that a quantum system is built on classical statistical mechanics. And if you believe that you have to do molecular dynamics or Monte Carlo for classical systems, then you're going to believe that you have to do it in quantum systems. There's no reason to think a quantum system would be simpler. What fools us is that a Hartree-Fock or density functional method seems to be so accurate that you think you can get away with that. But if you try to improve the accuracy of Hartree-Fock or density functional theory, you discover that it becomes very difficult to improve the precision of that. Whereas quantum Monte Carlo, we have like a systematic way we can improve things and get more accuracy. And that's what you'll learn some this week. So most of the quantum methods are based on Feynman's imaginary time path integrals that I'll talk about later on today and tomorrow. It is, as I said, the most accurate method for general quantum many-body systems. And there's a variety of different quantum Monte Carlo techniques. And we're going to mainly focus, well, we're going to talk only in this week about variational Monte Carlo and projector Monte Carlo. Variational Monte Carlo, these are both, I call zero temperature methods. That is, they're methods for a single quantum state. But there are quantum Monte Carlo methods, path integral methods, that work for finite temperature ensemble, non-zero temperature. But we won't, you can talk to me privately if you want, if you have questions about path integral Monte Carlo. I'm going to talk briefly on Thursday, I guess it is, about coupled electron ion Monte Carlo, which is kind of a specialized technique that that we've developed that incorporates some finite temperature aspects into quantum Monte Carlo. So that's a big picture quantum Monte Carlo. Now let's get back to the Monte Carlo part. This paper in 1953, there are 2 papers in 1953 that laid the basis of what we're going to talk about this week. This is the first one, the Metropolis paper. We call it Metropolis, but this is one of the unfair things in science. That is, the person that contributed the least gets the most of the credit. The other authors, the main authors, were the husband and wife team of the Rosenbluths, Marshall and Ariana Rosenbluth, who did most of the work, and Marshall Rosenbluth became later famous in fusion physics. But the most famous person on this paper is Edward Teller. If you ever saw the movie Dr. Strangelove, you may have seen who Edward Teller is. But that is, he was the crazy Hungarian physicist who invented the hydrogen bomb, or partly. He took credit for it anyway. But he actually was an important stimulus for developing this so-called Metropolis method, which introduced the idea of the rejection technique that I'm going to talk about now. So actually, they sort of formulated the Metropolis or method just physically. But nowadays, well, it was pointed out soon thereafter that Markov, a famous Russian mathematician, had actually developed this 100 years earlier in terms of Markov processes. And it's an example of a Markov process, which is one of the simplest statistical processes. Basically, you have the idea of a state space. In our case, it's going to be the electron positions and possibly their spins, but mostly just the electron positions. If you have a molecule or a solid, we have a finite number of electrons, like 100 electrons, say, and so the state space would be the coordinates of the electrons. So we're representing electrons as points. That's how we differ from other methods like quantum chemistry, where you might represent wave functions in terms of basis functions. We actually just represent them in points. That is, coordinates, XYZ coordinates for each of the n electrons. That's our state space. And so the Markov chain is just a game, a random game, where you move the electrons one at a time or all together with some probability. And that's what we call a transition probability. So P is a probability that you move from one point in state space to another. So this index here describes the Monte Carlo time, that is the iteration. So you start out at state 1, and then you move to state 2, state 3, state 4, and so forth. And a Markov process means you just have an a priori probability of moving from one state to another. That is, you have a rule. And Monte Carlo means that you use random numbers to decide what the move is. That's the definition of Monte Carlo. That is, you have random numbers somewhere in the process. Of course, on computers, the ones we use, you don't have true random numbers. You have what are called pseudo-random numbers. And they're very much like random numbers, but they have a deterministic algorithm. Okay, we won't worry about that. We'll assume that somebody has figured out how to generate these pseudo-random numbers. And it turns out that Monte Carlo is not terribly, this kind of Monte Carlo is not terribly sensitive to the fact that your random numbers aren't quite random. But in any case, the properties of transition probability, of course, it has to be positive or non-negative. That's something we'll come back to when we talk about fermions. And the fact that it normalizes to unity. That is, there's always a probability of moving somewhere, right? And the definition of a Markov process is that this probability density only depends on where you are. So sometimes we used to call this a drunken random walk, right? It's like an undergraduate, none of you are undergraduates, walking around town on Saturday night and have no memory of where they were or where they're going, right? East, west, north, south, they go some way, stumble around somewhere, and the question is, where are they at the end of the night, right? And so that's a drunkard walk, right? And with this, you can prove rather simply that under certain conditions, it goes to an equilibrium distribution. This is the master equation. You can write it as if f of n is the probability where the undergraduate is after n steps, what is the probability density in this state space? Okay, so you could easily see you have an equation like this. That is, the probability, if f sub n is the probability after n states, what is the probability after one more step? And it's going to be given by, the transition probability. And you can kind of recognize this as like an eigenvalue problem. So after, if you have as n goes to infinity, this has to go to a stationary state. So it's a solution to this kind of an eigenvalue problem. It's a little different than the eigenvalue problem in quantum mechanics because this P is not Hermitian. Okay, but still, most of the mathematics goes through. In fact, more of it goes through because you have these two conditions on this transition probability. And the only the only condition you have to apply to P is P has to be what's called an ergodic matrix. An ergodic means that the random walk has a finite probability of going everywhere in the state space. And in terms back to our undergraduate wandering around town Saturday night, well, imagine if there was like a river separating one side of town from the other that you couldn't cross the river, then that would be non-ergodic. You couldn't go to the whole town, right? Or if there was a wall, right? And so you have to make sure that your random walks are ergodic, and that's usually pretty easy to figure out. And in fact, this is where Monte Carlo differs than molecular dynamics. In Monte Carlo, you can prove that things are ergodic-wise, and Newton's equations of motion, it's a much more difficult mathematical problem to show that things are ergodic. But there are some, ergodic there's two aspects of ergodicity. One is the mathematical aspect, that is, can you go everywhere in a finite amount of time? The other is a practical aspect. If your random walk has say, 1 million steps, has your system converged after 1 million steps? That's hard to show mathematically. You have to use some common sense and look at things to make sure they're converged. And I'll talk about that in a few minutes. And computing error bars. So when we talk about ergodic or convergence, that's what we're talking about. Because a random walk is correlated. Namely, if you're looking at this drunkard walking around town, if you look at it 10 minutes apart, you can pretty much figure out where they are. If you look like a whole day apart, you may have no idea where they are, right? That's the correlation of their position. And it's the same in our quantum Monte Carlo. Now, the Metropolis algorithm builds on the simple properties of Markov chains by adding something called a rejection. And that was Teller and Rosenbluth's key insight. First of all, there's a property of random walks, of Markov chains, which is called detail balance. It should be familiar from statistical mechanics, that it describes a rate balance. Now, pi in this equation is the asymptotic solution to the equilibrium state. In our case, we want to specify what pi is. We want to say pi in variational Monte Carlo is the square of the wave function. Okay, so we know what pi is. And this equation basically says the flow of probability from state S to S prime is equal to the reverse flow. That is, this is the probability of being in state S, this is the probability to make a transition to S prime, and that's equal to the reverse rate. And so that's called detail balance in statistical mechanics. If you have detail balance and you have a Markov process, then you know that pi will be your equilibrium state, if it's ergodic. And this is the one-line proof of that. Now, what Metropolis did was enforce the detail balance by using rejections. And so you break up the, okay, here this example is pi of S is given by the Boltzmann distribution. That's a classical example, but we're going to use the wave function instead. But basically, you have an a priori state, which is given by T. This is the so-called sampling probability. An analytic function is T, and then you have an acceptance probability, A. Okay, so the probability of going from S to S prime is the product of T times A. So in other words, in terms of the drunken random walk, just imagine the drunkard is with a sober friend, student, and the drunken person says, I want to go this way, and the sober person says, well, no, that's not really a good idea to go that way. Why don't you stay here? Okay, so that's basically all the acceptance does. It says, with a certain probability, you stay in your current location. And what's used in Metropolis is this formula. And I won't say why, but this is the best thing to do. It says the probability of actually making the move is given by the ratios of the transition rate in the forward and the reverse direction, but capped at 1, because probabilities can never be greater than 1. So this is a so-called acceptance probability. This is something you compute. In the case that the transition probability is just a uniform distribution, it simplifies down to the ratio of the probabilities that you want to sample. Okay, and so basically the idea is, this is the so-called classic method, again illustrated for the Boltzmann distribution. You say you move from, it's very simple, you move from one state to another state with some, in this case, constant probability. That's why I call it the classic Metropolis, because the probability is constant. This is the general formula here, and this is the classic formula here, where you assume that T is symmetrical. And so basically, this is the probability of making the move. That is, you make a move from S to S prime, you see how the energy changes from S to S prime compared to the temperature in the classical physics. And if you go in a downhill direction, that is, you lower the energy, then this quantity will be, this will be negative, and you have a minus sign, so it's positive, so your exponential will be greater than 1. And so it'll be limited by 1. And so for sure, you'll accept the move. So the drunkard will always go downhill, right? If he decides to move downhill, it'll accept that move. But on the other hand, if you're going uphill, that is where the probability, this is positive, the energy difference is positive, then this will be, the exponential will be less than 1, and then you'll accept it with a probability less than 1. So if you go, say, something that is many times a KT uphill, then the sober student will say, no, you really shouldn't climb up that mountain. It's too much work. And you'll reject the move. And you'll sit there for one more cycle on the computer, and you'll try another move. Okay. And so the idea of the Metropolis, and so this is the basic scheme. And in fact, I have a flow diagram coming up here. And so you're given ergodicity, your distribution of states will be the canonical Boltzmann distribution. The convergence is guaranteed, but the rate is not guaranteed. You don't know how long it'll be till you sample the Boltzmann distribution, although you can make some estimates of that. So I kind of explained all this. This is the acceptance probability. And here is example, I'm illustrating that with some particles. So we have we have about 10 particles in a box. We pick up one particle. I'm sorry, I didn't fix this slide. This is supposed to be a delta here. And so we sample, pick up this particle, we sample it inside this cube here. We move, the cube is psi delta. Spring is our local random number generator. And so this is actually, it's a two-dimensional box. So we move in the x direction and in the y direction. And we say our new position, is inside this, is randomly distributed inside this black box, a square here. And we compute the new energy and compare it to the old energy and decide to accept or reject the move. So there's the new position. We accept or reject. Okay, here's some little bit of pseudocode. For a whole classical Monte Carlo code. Okay, so this is kind of what QMC Pack is doing when it's doing variational Monte Carlo. We have this loop. I don't say how big the loop is because it's actually, millions of steps. You just keep running. In fact, in my codes, what I do is I say, well, I want to see the results when I come in tomorrow morning. So I'll just put this loop to execute until tomorrow morning. It'll stop and it'll put out the results. So it'll do millions of steps, however many, it depends on how busy the computer is, right? And then you just collect averages, right? And so this is the loop. And so what is involved in the loop? S is the state space. So you have an old position and a new position, and you sample the new position with some transition probability. Okay, the 1 indicates you're going forward direction. You calculate the new energy or the new action, depending, if it's quantum mechanical, it would be the wave function. And then in the Metropolis formula, you have to do the backwards direction too. So you're actually not moving backwards. That's the difference between the argument 1 and 0. You're just finding what is the probability that you would have moved in the opposite direction. This is because of the detail balance formula. Then you calculate the acceptance probability. And so you have the old and the new energies. The old energy you save from the previous step. And then you have the ratio of the transition probabilities. I'm sorry, this bracket got somehow moved over. And then we have the acceptance probability. We compare it to a random number between 0 and 1. So the random numbers come in here, and they're embedded in the sampling function here. So that's why it's Monte Carlo. Okay, if it's greater than the random number, you accept it. And so what does that mean? Well, this very simple algorithm, there's only 3 things that you have to do when you accept it. First, you update your state space with the new one. So S old becomes S new. You update the energy with the new one that you computed already. And then you keep track of how many times you accepted it. That's very important, as I'll explain in a minute. In Monte Carlo, there's not very many things you have to watch out for, but the acceptance probability is one of the things that you have to keep your eye on. And then having accepted or rejected the move, reject means you didn't do this. You calculate the averages. And this is something when you write your own code that students often mess up on. They will only compute averages when they accept moves, but you have to actually compute them when you reject them according to probability. If you sit at a given position for 100 steps, that position counts 100 times. It's not just the number of new steps. So it's outside that bracket. Okay, the only part I didn't describe here was the initialization. And basically, that's, again, something you have to watch out for. The question is, when the drunkard starts out, where does he start out at the beginning of the day? Why is it important? Well, it's because when you're talking about a physical system, say you're doing an atom, just a hydrogen atom with 1 electron. If you start an electron off a light years away, it could take the life of the universe for that electron to get over into the physical state. Even though mathematically it's guaranteed to happen, that doesn't mean it's guaranteed to happen in your computer budget, right? So you started off, you give it a break. You started out in someplace reasonable, right? Where you want it to be. So, there's a lot of physics embedded in that initial state. And then, of course, you have to compute this E old because the recursive algorithm needs it, okay? So this is kind of an overview. I called it, instead of Metropolis, Markov chain Monte Carlo. That's actually what it's called in statistics, which has become a popular algorithm in statistics. You actually have choices in Monte Carlo. You can decide this transition probability, how to move from state to state. You have to decide how to initialize the state. We talked about ergodicity means there's some warm-up time or equilibration time. I'll give you some examples in a minute. You have to throw out the first states, and then you have to collect statistics, and you have to compute error bars, okay? I talked about this error. Sometimes people invent methods, new Monte Carlo methods that are more efficient, but you have to obey this rule that if you can move from one state S to S prime, you have to be able to make the reverse move also. That's a common error. Here's an example about the acceptance probability. Here, P is the acceptance probability. That's the probability that when you sample, that you accepted the move. And this delta is how far you move, okay? And this is the general trend always. That is, if you move a very small distance, you always are accepted. Okay, why? Maybe I should ask the audience here before you fall asleep. Why does this go to 1 when delta goes to 0? It's a very simple reason, yeah?
Change in energy would be very small.
Right. If you look at the acceptance formula, it's e to the minus delta, the change in energy divided by kT in the classical case. If you don't move, then delta, the change in energy is 0, and so the exponential of 0 is 1, and you're going to be accepted. Okay. But it goes to 0. It doesn't always go to 0 at large delta, but it usually goes to 0. Why would it go to 0 at large delta? Just to go back to, it depends on the physics to some extent, but why would it? This is an example of a liquid like water. Suppose, well, I don't know. Can somebody say why? Yeah.
Is it based on the
No, it's not based on that. It's based on the change in energy. That will give you a big clue. Yes? Oh.
remember to use your microphone?
Oh yeah, you use your microphone when you ask the question.
Well, I didn't want anyone to hear that.
Well, it could be the right answer. Maybe if you amplified the answer, you get, but anybody else? I mean, suppose there was a bunch of water molecules. You moved around, you moved the water molecule, yeah?
Would that be like you'd have like a vacuum if you moved far away and you'd increase the density by a lot somewhere else, wherever it ended up?
Yeah, you're going to
Something.
definitely. I mean, basically, if you take a strongly correlated system, he said, I don't know if you could hear that in the video, but he said it changes the density. You move a water molecule from here to here, you're making a vacuum in one place and a high density when you moved it. And that's unphysical, right? Basically, usually when you move a particle like that, you're going to end up on top of another water molecule, and that's forbidden by chemistry, right? You can't have two water molecules in the same place. And if you move too far, that's usually what happens. It's not always. If you have a gas, it wouldn't happen. And a gas, you have lots of free space, and you can move it. But we're not so interested in doing Monte Carlo gases, because that's not a hard problem. But so that's why usually you have this. And so you usually have a curve like this, where if you move it too short, you have the acceptance probability of 1, and too large, it's 0. But if the probability of accepting is 0, you haven't gone anywhere. You haven't gone anywhere either down here or up here. So the answer is, don't have acceptance probabilities of 1 or 0. Stay in the middle, acceptance probabilities of 1/2. That's what you always learn. You should have acceptance probability of 1/2, but that's not actually the rule. The rule is stay away from 0 and 1. And here is actually the error as a function of delta. The same, this is the error bar, and you see that it has a very broad maximum. That is, I'm sorry, this is not the error. This is the diffusion constant. This is how far you move. And so you want to move as far as you can. And this delta for, in this case, moving this distance, which is a 0.16, I guess, right here, is the optimal place, which is like an acceptance of probability of a half. But you see, it's a very broad maximum. As long as you're in between, I say between 20% and 80% is the actual rule. You don't have to be 0.5. Okay, what's your question back there? Use your microphone.
Suppose we are just at an unstable point, like the top of a hill, and we make a very, very small move. Should we still accept that move?
You're at the top of a hill. That means no matter what you move, you're going to accept because you're always going to go downhill.
Oh, but what about the reverse situation then?
If you're in a deep valley,
Yeah, and we make it.
you're going to always be rejecting moves in a deep valley. That's why systems form solids, right? At low temperature, systems go to a place that minimizes the energy, and they don't want to move out of that. And they only move. We're talking about classical statistical mechanics, but everything in quantum Monte Carlo eventually goes back to classical statistical mechanics. So that's why I talk about it. But if you're in a deep valley like this, you have to put in the temperature, right? So actually, I guess I can use this board here. Let me start using it. So, you're in a valley like this, and of course, at zero temperature, it wants to be here, right? But there's some temperature T. This is KT, classically, and you're trying to sample this distribution. So it will let you, the Metropolis algorithm will let you go in this region here, but it's not going to let you go over here because that energy is much greater than KT. So you accept with this probability here, well, delta E over KT. And that will mean your distribution, it will stay in a region, well, since I drew a harmonic oscillator, it will actually be a Gaussian distribution, and it'll stay there naturally in this region. But it will not let you go way up here because that energy is much greater than KT. Okay? Yeah?
But how can you guarantee ergodicity? I mean, if you have two valleys and you will only stay like...
Okay. Again, there's two different questions about when you say guarantee ergodicity. You can mathematically guarantee ergodicity. That's not a problem. The problem is to guarantee it in your actual calculations. That is, just like the example I gave you, they will converge eventually, but you just don't know how long it will take to converge. Now, if you have, so your example was a double well like this. The question is, you start off here, can it go across the barrier to get to that other side? And mathematically, it will do that because there is a finite probability, no matter how big this barrier is, of going across. But it may take 1,000,000 steps to go across, or it may take 10 to the 20th steps, and you'll never be able to do that on your computer. So that's where the physics come in, and you have to understand the problem in order to guarantee that. Now, Monte Carlo is a very general approach, and we are allowed to make moves to go directly from here to here. We do not have to take moves like you do in molecular dynamics that are local. If you can make moves directly from here to here, you don't have to tunnel across the barrier. And you're allowed to do that, but you have to understand first that barrier exists, and this could be a problem. That's where your intuition about the problem comes in. I don't know, does that answer your question? Yeah. Any other questions? Yeah?
Yeah, your slides disappeared, but I had a question about your
Oh.
figure on the acceptance.
How did I do that?
I think your screen's
Oh, okay.
But so for this figure of the acceptance probability as a function, delta is the cell size, right? And sigma is,
Yeah.
is the
Yeah.
variance in the energy or something, standard error or something?
No, the sigma is this is a Lennard-Jones potential. It's just the scale, the size of the potential.
Well, my question was, like, a priori, how do you know? Is there a way to figure out how big to set these things so that you can get the right acceptance ratio, or is it something you have to test?
Both. That is to say, on your problems, you're going to be doing electronic structure. Does everybody know what the atomic units are? Atomic units are where h bar and m are equal to 1. And it's like 1 Bohr radius. Does everybody know what a Bohr radius? That's the unit of length. So think Bohr radii. I mean, basically, if you move particles that are like 1 Bohr radii, that's a reasonable starting place. But then you look at the output of the computer code and you see what your acceptance ratio is. And if your acceptance ratio is 10 to the minus 3, does that fall into my criteria between 20% and 80%? No. That means you're going to be, you're way down here in the curve, and that means if your acceptance ratio is 10 to the minus 3, that means you're doing 999 moves before you accept one, and that's obviously inefficient. You're trying. It may be inefficient, but actually sometimes we do that for good reasons. And similarly, if your acceptance ratio is 99%, that means you're really taking little tiny moves in phase space, and it's going to take a long time to get anywhere. You really should take much longer moves, or at least try it and see if it works. So as I said, there are not too many things that you have to do in Monte Carlo, but acceptance ratio, you should be looking at more than the ground state energy as the output of your computer calculations. The ground state energy, its error bars, the acceptance ratio are the first 3 things that you look at. But there are more things that I'm going to talk about that you look at. Computer code is kind of like it's kind of like driving a car or something like that, where you have a lot of instruments and you have to look at the instruments and see what you're doing. Yeah?
So is it possible to introduce some extra error if you have a different step size?
No. Okay. That's one of the tests. That's a good question. One of the tests of Metropolis, the question was, can you introduce an error? Okay. First of all, we have to say, what's an error? There's 2 types of errors that we distinguish. There's systematic error and there's statistical error. Okay, systematic error means even if you run forever, you get the wrong answer. Statistical error means that you have just statistical fluctuations, and the longer you run, the smaller that they will get. We're going to talk about that next. The step size should only give you a change in statistical error, should not give you systematic error. This is one of the tests that we use in Monte Carlo, is to make sure that the results are independent of the step size. You should be able to run at 20% acceptance probability, 40%, 80%, do long runs, and they should agree within 1 error bar. That's a test that we use. You see, in Monte Carlo, it's not like LDA calculations or whatever. You just don't get just 6 decimal place accuracy, machine precision or whatever to compare. You just get something within an error bar. So you have to use other tests to make sure your code is correct. Any other questions? Actually, this is a follow-up on the same graph. This is actually the error bar. Somebody asked if sigma was the error bar. So this is the error bar, And you see why I say that you have a whole range of error bars you can use. You should get the same efficiency. You know, the error bar, this is really 40 years old, this graph, but there's probably better ones. But this is kind of typical if you do it, that you know, you get some sort of confusing graphs, and this is not what you should be focusing on the Monte Carlo of getting the most efficient algorithm. You should be focusing back on what the physical results are, not on the efficiency of your code. Anyway, okay, now this is the change the topic. Well, this is what transition rule should you use? Any transition rule is allowed as long as it's ergodic, okay, first of all. That is, it's allowed in the mathematical sense. But the question is, what is the most optimal? If you use a very bad transition rule, you'll need more steps in your Monte Carlo. And you could ask, what is the best transition rule is? Well, the best transition rule would be one where you sample directly the distribution, which I call pi of s, that you want to sample. There's been, back in the 70s, some methods to improve over the classic Metropolis. Instead of moving randomly, uniformly, that is, remember my picture here where we moved uniformly inside a square? Well, instead you use the forces, which is the derivative of the energy, to push you in a direction, in the downhill direction. So like the drunkard is walking around, it's not flat like Champaign-Urbana, but it's on a hillside, and you preferentially move in the downhill direction, right? That's the force. The force is the gradient of the potential. Okay, so for example, you could set this transition probability to do a Taylor expansion in terms of the potential, and you move in the downhill direction, there's a normalization constant. And something like this is what we use in variational and diffusion Monte Carlo. That is, we don't sample a uniform distribution, we actually sample a Gaussian distribution, and it preferentially goes to places that increase the probability of the wave function. And that's to get a higher acceptance probability. And actually, that's kind of what these graphs were showing back here. These are different types of bias, sampling bias. And so the lowest one was the classic Metropolis, and this graph was showing that if you use force bias, for the same delta, you can get a higher acceptance probability. And then you can go over here to the efficiency of the random walk. Well, you have to remember what the symbols were here. The smart Monte Carlo, the squares and the triangles over here, so you can get a higher efficiency by using this. Well, this is actually the autocorrelation of the walk. You can get it decorrelates faster if you use these improved methods. Okay. So I say one of the advantages of simulation is it's an exact method to do a many-body problem. It's not exact in the sense that when you solve the hydrogen atom in elementary quantum mechanics, you get the exact result. It's exact in our sense is if we average over a sufficiently long random walk, we can get arbitrarily close to the exact answer. That is, and luckily, computers have gotten faster and faster, and we're able to do this in practice. We can run for 1 million hours, and we can get really accurate results if the code is correct. Now, simulation results without error bars are useless. If you come to somebody, your advisor or your the referee of your paper, you say, I got this answer for the energy, and it does not include the error bars, it should be rejected without even looking at the paper. Okay, it's not like DFT calculations, so presumably they've checked all the convergence. You have to know what the error bar is, and you have to understand how it's determined. The error bars are determined internally in the calculation from the fluctuations. Essentially, I mean, now that we have parallel computers, we can imagine we repeat the calculation on 1,000 processors, and we get 1,000 results, and they should be uncorrelated, and you use the standard formulas from statistics to figure out what is the distribution. What is one standard deviation? That's what I mean. They're determined within the calculation itself. Okay. You should be able to understand the formulas and make an eyeball estimate. I'm going to give you this example here in a minute, but here is what I call the trace of a Monte Carlo, and this is the kind of thing that you should be looking at in your calculation. And there's some tools that you'll learn about this afternoon, right, Jaron, that tell you how to look at these things when you're doing it. Okay, so what are we looking at? This is the energy of a classical system, and this is Monte Carlo time here, iterations. We have 5,000 steps, right? And we just plotted out the instantaneous energy for 5,000 steps. This is a histogram that shows what's the distribution of energies. And this part here is what we call the warm-up. This is the influence of your initial conditions. We started out in a very nice place, and you see it dropped down to what we think is the correct answer, probably within 100 steps. But because it didn't matter, we threw away 500 steps. So you throw away the initial warm-up part. Why? Because if you leave it in there, it puts a bias in your results that can take a long time to get out of, okay? But without, I can't tell you how many steps you have to, because that depends on how you started and how you move the particles and what the system was, right? That's the so-called equilibration or warm-up. And then we have this long thing where it's stationary, namely it's just going up and down, and so forth. And we use that to compute the error bars and the mean, right? The error estimates are based on the central limit theorem. The central limit theorem has conditions on it. It is a theorem. It says, let's see, do I have a graph? Oh yeah, I have a explain the central limit theorem. If you sample n independent values from some distribution, you calculate the mean as the average value over those values. This is actually the proof of the central limit theorem, which I won't bore you with, but you can prove it using Fourier transforms. But given enough averaging, almost everything becomes a Gaussian distribution. So y is the average variable, right? And so what is the distribution of the mean? This is the distribution of the mean, and it's a Gaussian. It doesn't matter what the distribution of the x's are. Well, it does matter a little bit. Does anybody know what properties of the x's you need? Has anybody studied probability that much?
Finding variance?
You have to push your button.
Yeah.
Push your button there.
So, have a variance?
That's right. That's right. Finite variance. That is to say, you have to assume that the x's have a limited distribution. They don't have long tails. We're going to look at that in a second. But as long as your variance of x's exists, then the y's have to go to this distribution. And the error of y is sigma is given by the square root of the variance of the distribution divided by the number of sample points. So this is both the saving grace of Monte Carlo and the disaster, right, at the same time. First of all, you will, if n goes to infinity, you will get the exact result in a probabilistic sense, right? You'll be very likely to be within 1 sigma. On the other hand, sigma decays as 1 over the square root of computer time. So in order to get 1 more decimal place, you have to run 100 times longer. To get 2 more decimal places, you have to run 10,000 times longer. Or do something else, or be more efficient, one of the two, right? So that's the standard thing. Now the thing that I left out, that this is a simplification that confuses a lot of people, is I assume that x's are independent samples. And in Metropolis Monte Carlo, they are not independent. They are correlated with each other. And some people say, well, that means I can't do it this way, but that's not true. Let me explain. Okay, here's an example of how things approach normal. Suppose you sample a square distribution, and then you added 2 numbers together to make a new number. It would go to a triangle distribution. If you added 3, it goes to this quadratic function. If you add 4, it becomes indistinguishable with a Gaussian after 12 of them. So that means things approach a normal distribution very fast if they have a finite variance. We explained this already. Depends whether the central limit theorem is obeyed depends on the variance. This isn't, okay. You're going to be using QMCPAC, and presumably it's been done okay, so we have a finite variance, we hope. But it's perfectly possible to do a quantum Monte Carlo calculation with a bad wave function that will have infinite variance. And that means your error bars really are not, in the mean, are really not necessarily correct. That's where physics or chemistry come in. You have to have good wave functions. That is, they have to satisfy finite variance. And usually, you get infinite variance because of 2 things that could happen. The first is the tails of the distribution. If one of the electrons can wander off to infinity, that could give rise to infinite variance. Like if you have a molecule, in a bound state, the electrons are supposed to be localized around the molecule. If you give a wave function which doesn't go to 0 in infinity, that electron is going to wander off, and there'll be infinite variance, probably. That's the problem with infinity. The problem at finite x is, for example, at x equals 0, when an electron is, say, on top of a nucleus, the potential energy diverges at that point, goes to minus infinity. Hopefully, your wave function has the right cusp, so your energy won't go to minus infinity. That would be an example of a singular behavior at finite value of r. But if you obey the cusp condition, we'll talk about that later, then you won't have that. You'll be okay for this. Your distribution will be finite. This is the reason why it's hard for us to compute forces in quantum Monte Carlo, because it's infinite variance. Forces the naive way of doing it is it gives you infinite variance. Okay. Here is again the trace of two different runs here. And this is uncorrelated data. I just want you to look at it. And this should look like white noise to you, if you ever looked at white noise, right? It's just going up and down very quickly. This is 1,000 steps. Can you see the difference with this over here? If you look at this carefully, you see it's going down and up and down and up like that. What's shown here, I don't know if you can see it, maybe it's a good idea. What is the autocorrelation time? That's an important number. That is, how fast does it go up and down? This data is uncorrelated, so by definition, its autocorrelation time is 1 step. That is, every step is independent. This, well, I won't make you guess, but you can see this feature like takes 100 steps. The autocorrelation time is actually 11 in here. It's been computed to be 11. What is the definition of autocorrelation time? Well, maybe you study this in stat mech. What's a correlation function? It's the fluctuation at one time times the fluctuation at a later time, averaged. That's the autocorrelation. I'll write down the formula in a second. This is actually the autocorrelation function. So it starts out at 1. Things are perfectly correlated. If they're if they're 0 steps apart, or if they're 1 step apart, and then it decays down to 0. The autocorrelation time is defined as this integral of this area here. I'll show you why in a minute. In the uncorrelated data, it's basically a delta function at 0. And so its autocorrelation time is 1, and in this case, it's 11. So it's the area under this curve. Why is that autocorrelation important? This goes back to your efficiency of the random walk. If your data is highly correlated, statistically, it's not independent of each other. And in the formula, in the central limit theorem, you're not allowed to divide by the number of steps. You're only allowed to divide by the number of uncorrelated steps. Just, basically, you don't have 1,000 independent steps here. Instead, you have 1,000 divided by the correlation time, which is 11, which is like 100 steps, roughly speaking here. So you only have 100 independent values. So this means your error bars are the square root of 11 times larger. That is about 3 times larger. If the fluctuations here were the same here and here, this error bar in your mean is larger, because your sampling efficiency is not as high. It doesn't mean that you don't converge to the right answer, or that you don't eventually converge to the right answer. It just means your code is running slower. So you have to run it longer, and you have to know that to compute the error bar. But you'll learn this afternoon on how you run the tools to compute error bars. But you have to know what the answers are. Well, this is interesting. I don't know what happened to that slide. That's too bad. Oh, well. What's that? That's all right. I can just use these. Well, I don't know. We kind of talked about that. I don't know really what happened to that slide.
Online, it's on, so students can see it.
Okay.
It's just here.
I don't know. PowerPoint did something. Okay. Here is the mathematics, so you can do, maybe you've seen this already. How am I doing on time?
It's 10:25.
So, okay, good. Anyway, the mathematics is not very complicated to prove what I said. This is the definition of the correlation time. The correlation function, I said in words, is given by this. A is the property that we're trying to estimate, like the energy, but it could be any property. And delta A is the fluctuation from the mean value. And the angular brackets mean average over an infinitely long random walk. So this is the definition of the correlation time. that I was showing you in those other graphs, the autocorrelation time. And we want to calculate what the error bar is, the mean value is. That is, what the mean value is our estimate over the entire random walk. And so, this is the definition of the error bar, okay? And this is the formula that we end up with. That is, the error bar is given by the autocorrelation time. And this is the sum of the fluctuations in your sample, and then you divide by essentially n squared and take the square root. And this is essentially how we compute error bars, right? Now, one wrinkle might be, if you're doing things in parallel, runs on different processors are really uncorrelated with each other. And so you might have another formula where you would take error bars on each processor and combine them together with the independent error bars. But that's just another complication, which is done automatically. And this comes out of this basically some algebra, which I don't think is that useful to go through. But the only property that you're using is the fact that the Markov chain long enough becomes uncorrelated. Eventually it has to become uncorrelated. And you can ignore things that happen at the beginning and the end of the random walk. So this is this little graph here is showing t and t prime summed over 2 points of the random walk. T and t prime, they're like times, and you're extending the sum to include the part that you didn't do. But anyway, eventually you prove the formula. So actually, in response to a question, I explained the difference between statistical and systematic errors. Statistical errors measure the distribution of the averages about their average value. The statistical error can be reduced by extending and repeating the runs. That is, we increase n. That's really an important feature. If you come to me and say, well, my deviation, I'm deviating from the textbook results by 2 sigmas. Does anybody know what is the probability of that happening, a 2 sigma deviation? That's 1 sigma. Close. Just square that. It'll be about 10%.
95.
What?
95.
95, good. Yeah, approximately. So 2 sigma. So what should you do if you're concerned about a 2 sigma deviation? You still have the computer sitting there. You should just run it longer. I don't even want to talk to you. I would say just run it 10 times longer. Usually computers are just sitting there idle all the time. Not always, but I mean, if it's really a concern to you and you're sitting there scratching the head, should I be worried about 2 sigma deviation? Well, you see, if you run it longer, say you run it 10 times longer, your error bars will decrease by a square root of 10, right? 3. And a 2 sigma error will either go to a 6 sigma error, and I would be definitely concerned about a 6 sigma error, or it'll go to a 1 sigma error, and you had nothing to worry about. So you have to use the computer as your tool, right? And not just sit there, because there's no way, there's no way to know whether a 2 sigma error bar is real or not. So that's statistical error. The efficiency is how we measure the rate of convergence. So the efficiency, psi, is 1 over the computer time, this is computer time here, divided by your error bar squared. So the point of this combination, you see, because this goes like 1 over n, is this efficiency doesn't depend on how long you run it. So, you can improve the efficiency by having a faster computer, a faster algorithm. It depends on the property you're calculating, the wave functions. So this is how you measure. Like somebody says, my code is better than your code. Well, the comparison is the efficiency, right? You calculate how long it took, what the error bars is, and this tells you the efficiency of calculating a given property on a given computer with a given algorithm and so forth. Systematic errors are the ones that you have to be concerned about, and those are the other errors, and we'll talk about that some more, but there's a lot of systematic errors. Like fermions have the so-called fixed node errors, pseudopotential errors, finite size effects. These are going to remain no matter how long you run your code, right? You have to do some thinking about how to get rid of those, some other things. But statistical errors are sort of the unique thing of Monte Carlo, because quantum Monte Carlo is unique in that we can estimate the errors within the calculation. We don't have to go outside. Like DFT, you never know what your errors are, really. You know for a given functional what the result is, but you don't have any internal way of finding the errors. You just have to compare to experiment or something. So one of the important things is that you develop vocabulary, because otherwise I would be talking to you and I don't really know what you're talking about, right? That's because it can be confusing if you use the words the wrong way. I told you what the trace is. The trace is the history in the Monte Carlo. That's a good thing to look at. Equilibration time, I explained. That's the warm-up time. The mean value of the property, that's the mathematical correct answer, is the mean value. The variance, this is how much it fluctuates. Here, you see this property fluctuated, and it says right here what the variance is. It says it's 0.1. See, it fluctuated from like minus 7.3 up to minus 7.2 or something. It fluctuated 0.1 here. This is the variance. That never goes away. This is sometimes confusing. This, you could run for an infinite number of steps and it would still keep fluctuating forever and ever, right? But what doesn't fluctuate if you go on for a long thing? That's our knowledge of the mean value. That's what we learn, and that goes like 1 over the square root of n. So that's why things get confusing, right? We estimate the mean, and we have the estimated error of the estimated mean. This is what our error bar is, right? Well, our error bar wouldn't be estimated, it would be the error of the estimated mean, but we have no way of knowing what the true error is, so we have to guess what the error is. We have to understand that the mean value has some fluctuations and the variance has some fluctuations. It's actually bigger. But anyway, this is the error bar that you quote, the error of the mean, right? The efficiency I explained, the autocorrelation of the property I explained, the correlation time I explained. So anyway, this is the vocabulary that we have to agree on, otherwise we can't talk to each other. Statistical thinking is a little bit different, and if you've had statistics, you should know this, but you don't. People kind of forget it. I just explained this. Shouldn't the energy settle down to a constant? No, the energies, they fluctuate forever. It's our knowledge of the mean that settles down, of the average, right? Some people think because the data is correlated, the central limit theorem is invalid. That's not correct. You just have to correct for the correlation. Data set A differs from B by 2 error bars, therefore it must be different. Well, we just explained that. This is where statistics it can be a confusing subject. If I have 2 results, like code A and code B, and I compare 10 different properties of code A and 10 different properties of code B, there better be some 2 sigma differences. In fact, this is a classic case, something almost always happens. Suppose we compute a curve like this. This is some property, say dipole moment, or just arbitrary property. I'm sorry, this is I don't know. Anyway, we're computing something. Say the energy versus density. And suppose we get this result. Like this is density and this is energy. What's wrong with this figure? What's that? I would look at that and I say, you made a mistake. That's wrong. It's completely wrong. Something's wrong here. What's that? The size of it. What's wrong with that, though? What's wrong with, are you pushing your button?
I don't understand what you are graphing.
Okay.
The error bar normally goes up in one side and smaller to the other side.
No. This is energy versus density. It could be any property. We're varying one parameter. We're calculating. And I'm sorry that you may be worried about my artistic abilities here. But those are the points and those are the error bars. The sigma error bars.
I think it's too linear.
Exactly. It's too linear. I know you cheated. It's like finding that somebody cheated. You could theoretically, draw a line through here. There's 7 points here. There should be some 2 sigma errors. If there's not 2 sigma errors, I know either you threw out points that were 2 sigmas off, or you increased the size of the error bars in order to, because you weren't very confident about the errors. But the true curve should have some points like this in it. This is why they caught a lot of these famous people that fudged the results in science. A human can't make things look random. Humans always like to have things orderly, right? So and the mathematical way of proving this is what's called a chi-squared test that you should have learned. And that they could say the chi-squared for that first graph that I drew was completely wrong. That is, it was very improbable that all the points would be described by a line that goes right through the error bars. Right? So here is something I often hear is, my calculation, it's too difficult for me to compute error bars. Well, that's too bad. You're in the wrong field. I don't know. You can always compute error. You always have to estimate error. Even if you give a bad estimate of error bars, you have to give some estimate of error bars. And the reason why it's usually too complicated is you're calculating some property in the code, and then you have to do all sorts of mathematical transformations to get the number that you want, right? Like I was saying, you fit that to a line, and you really wanted the slope of the line. Well, that's an easy thing to compute error bars of. But there are ways of doing that, and you have to learn how to do that. And there's always one way to do it, which uses computer time, and that's simply to divide the whole calculation into 10 subcalculations and do the whole procedure 10 times and seeing how much your answers fluctuate. That always works, but there's better ways to do it, but that's always one way. You always have to be able to. If it's important enough to put in a paper, you must estimate whether the results have any significance or not. You have to calculate, at least roughly what the errors are. Okay, so I guess I didn't say this and this relates to one of the questions we had earlier on, is how long do you have to run and to estimate error bars? If you're doing a calculation, and suppose that you have, say, the energy versus, this is computer time or iterations here, and suppose it comes down and you stop there. That's what I call a badly converged run. At best, this part is the only good part of your data. But as I say here, you need at least 25 data points to estimate error bars. So at least you have to run that long, right? Because you can see that this is something like your correlation time, and you need 25 correlation times. Why 25? Well, it's like the error of the error goes like 1 over n, and square root of 25 is 5. That means you're estimating 1/5 is 20%. That means your error bars are good to 20%, right? Which is, okay, at least the error bars have some significance. So, if you just showed me that, I would say, well, it looks like it might be converging, but go back and run it much longer, because you see what could be happening is this thing could be continuing to go down like that. You just cannot stop at this point. So this is what we call a well-converged result. That is, you estimate the correlation time, and then you run occasionally 25 times longer, once in a while. If this is a parameter study where you're studying a parameter, maybe only one of your data points do you really see, has it converged or not? And you have to occasionally do that. So anyway, any more questions? We're going to switch into quantum mechanics now. Any more questions about statistics? We could break. Is it time? Yeah, okay. So, but first of all, questions?
Yeah, for the correlation data, for the figure of the correlation data, I just don't understand why it's all above 0, because usually the autocorrelation function.
It doesn't have to be above 0.
Your figure is all.
That's the way it came out. Okay.
What's the property you did for the autocorrelation, like velocity?
Okay. You're talking about this figure here.
Yeah.
You're talking about this. This can go negative. There is one special thing about it, one confusing thing. This is the important part right here. This is just noise. And so when we compute the autocorrelation time, we have to cut off the summation and not include this part, because this is just noise out here. And it could go negative. You were asking, I think, what property were we computing? I think this was just the energy. This is the energy correlation. But it doesn't, well, I was just illustrating in general. Any other questions? So that's kind of a kludge that, I'm sorry, I don't know if that's a word. This is kind of a hack in the code, is that in the summation, when we calculate this correlation time, this is the mathematical definition. It goes out to infinity. You cannot, in practice, go out to infinity. You have to, what we do is determine it self-consistently, I believe. Actually, I don't know what QMCPAC does, but you kind of estimate what kappa is, and you go out to 5 kappa self-consistently to cut it off, because if you go out to too large of times, you'll just be putting in noise, and your error bars will end up garbage. But that's something that I can give you. You could have problems. There's another procedure called blocking, which we mostly use in the code. What blocking does is takes a run like this and divides it into, we compute the error bars assuming it's uncorrelated. Then we combine the data pairwise. Is this what we do? We add 2 data points together. We compute a third data point, and we compute the error bars again. And then we study the correlation as a function of the blocking factor until we converges. Unfortunately, I don't have that. It may have been on this graph that disappeared. But anyway, the blocking procedure is an alternative procedure to the correlation time. Correlation time is more precise mathematically, but is a little more delicate. Any other questions? Okay.